Last class we have discussed about molecular orbital theory. In that we have seen that there are two types of molecular orbital, that is bonding and antibonding, and we know the types of bond are two types, that is sigma and pi. So in today's class we are going to discuss about how to fill this molecular orbital and the molecular structure of simple molecules and bond order, magnetic character and calculation of bond order. These much things are we are going to deal about. So as we discussed earlier, we have said that this molecular orbitals are filled as same as atomic orbitals. For example, we know for filling atomic orbital there is an order such as 1s, 2s, 2p, 3s, 3p, 4s, 3d, such as a order is there. Similar to that, if we check our molecular orbital, there is an order. The order is for simple molecule such as up to nitrogen. We can tell this is the molecular orbital order, filling of electron based on this order. First sigma 1s, sigma 2s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, then pi 2px, that is equal to pi 2py, then sigma 2pz, after that pi star 2px, pi star 2py, then sigma star 2pz. This is the order of simple molecule up to nitrogen molecule. After that if we take oxygen, fluorine, neon, etc., the order there is a difference in the order. That is, only one difference is there. Instead of this pi 2px and pi 2py, we have to fill with sigma 2pz before filling pi 2px and pi 2py. This is only difference. It is a hypothetical concept. Okay. Then we'll move to next thing. So it is the order, and there is a very important property that we can understand from filling of molecular orbital, that is bond order. So what do you mean by bond order? So we can calculate this bond order by an equation. It is defined as half of the difference between the number of electrons in the bonding molecular orbital, that is can denote by the letter Np, that is the number of electrons in the bonding molecular orbital minus it is the difference between the number of electrons in the antibonding molecular orbital by 2. That is, we can define it as it is half of the difference between number of bonding molecular orbital and number of electrons in the bonding molecular orbital to antibonding molecular orbital. So it is the definition of bond order. So what is the significance? What are the significance of this bond order? From bond order we can understand certain matters about a molecule. For example, stability. We can predict the stability of a molecule based on bond order. If bond order is positive, then the molecule is stable. So vice versa, if bond order is negative, molecule will be unstable. If bond order is positive, then it is stable. If bond order is negative, it is unstable. So while seeing this bond order, we can predict the stability of a molecule. And the next significance is Bond dissociation energy. This bond dissociation energy is directly proportional to bond order. So if a molecule having high bond order, we can say that the molecule having high bond dissociation energy. For example, bond dissociation energy means the amount of energy required to break the molecule into its constituent atoms. So if while seeing the bond order, if a molecule having high bond order, we can say that there is a large amount of energy required to break the molecule into its atoms, its constituent atoms. So it is the relation with bond order and bond dissociation energy. And the bond length. Bond length is inversely proportional to our bond order. So if a molecule having less bond order, then the molecule having high bond length. So for example, if you take nitrogen molecule, it's having bond order 3. Oxygen molecule having bond order 2. So compared to oxygen, nitrogen having less bond length. So we can predict such properties of a molecule while seeing its bond order. The next topic is it's also very important topic, that is magnetic character. All molecules having its own magnetic character. How can we understand or how can we predict the magnetic character? If a molecule having unpaired electrons in its molecular orbital, we can say it is paramagnetic. It is paramagnetic in nature. If there are all electrons are paired, then we can call it as diamagnetic. If unpaired electrons are there, then paramagnetic. If paired electrons are there, then diamagnetic. Then we'll see how to calculate the molecular the bond order, and how can we predict the nature of the molecule, the bond order, etc. For example, if we take a very simple molecule, we'll start from the simple molecule. We know the simplest one is our hydrogen. So in order to write or in order to calculate this, there are several steps. The first step, we have to write the electronic configuration. So one hydrogen having 1s1, another hydrogen having 1s1. So it will combine, both will combine to give our sigma 1s. So one electron from here, that is here also one electron, here also one electron, they'll fill. So it will fill in one electron from here, it is combined and it is also combined together give sigma. So 2 electrons are there, it is sigma 1s2. So hydrogen having sigma 1s2. So from this we can calculate our what about antibonding? Sigma star 1s. No electrons are there. No, already only one electron is there in with the one hydrogen atom. So no more electrons are there. So what we can say, though sigma star, that is antibonding orbital, is 0. There is no antibonding, only bonding. So based on this we can calculate our bond order. How can we calculate? There is a formula, half Nb minus Na. So putting these values, how many electrons are there in bonding orbital? 2. So 2 minus antibonding 0. 2 minus 0 by 2, that is 1. So the bond order of hydrogen molecule is 1. So what is the magnetic nature? It is not having unpaired electron. 2 electrons are paired. So hence it is diamagnetic in nature. This is diamagnetic nature. So these things we can identify using a filling of molecular orbital. Then we'll see with molecule H2 how to draw the molecular orbital diagram, energy diagram. So in the y-axis there will be energy. Y-axis we have to write energy. And x-axis, the atomic orbital, molecular orbital will represent in x-axis. So here will atomic orbital. So for first one atom, we know atoms are combined to form molecules, so two atoms we have to write like this. Then molecular orbital depict here. If we take H2 molecule, we know 1s1, 1s1. So here atomic orbital 1s1, atomic orbital 1s1. Then we have to represent it in the 1s1, only s1, no. So s1, one electron is here, one electron is here. So if we take this, we'll check the combination. So we know bonding molecular orbital having less energy compared to its atomic orbital. So sigma 1 is here, sigma star 1 is above. Like this we have to draw, and 1s1. So one electron from here will combined. So we can draw the combination like this. One electron from here, okay, one electron from here, one electron from here. So it is paired. So it became sigma 1s2. What about antibonding? Is there any electron left? No. So there is no electron in the antibonding orbital. Like this way we have to draw the molecular energy diagram. This was simple molecule, and we'll move to another molecule called N2, nitrogen. We'll see what will happen with nitrogen. N2. So N2 molecule, same energy in y-axis, same molecular orbital, that is we know the electronic configuration 1s2, 2s2. What is that? 1s2, 2s2. We know the atomic number is 7, 4, 1s2, 2s2, 2p3. Like that all atomic orbital we have to draw. That is 1s, 2s, 2p. Same as one atom we have to draw with the another atom. 1s, 2s, 2p. 2p, p will be px, py, pz. Here also px, py, pz. So here is atomic orbital. I hope you know this one. This molecular orbital is here. So sigma 1s. Here we know 2s2. 2s2. So one electron from here, one electron from here. So two electrons are left. So in the antibonding, sigma star 1s2. Similar way we have to draw like this. Then here will come sigma 2s, sigma 2s. Similar, here also we have to fill, here also we have to fill sigma 2s, and sigma star 2s also we have to fill. Sigma star 2s also we have to fill because there are electrons left. And if we see, the all will be in the same diagram, but there is, due to insufficient space, I am showing 2p alone here, but all should be in same diagram, same space. 2p will be like this. So 2p3, 2p3. So 2p. So atomic orbital will be 2 you have to draw because there will be pi bond and sigma bond. And Px and Py always form pi bonds, pi Px and pi Py, and above that we know the order, like simple molecules first have to fill in pi 2 Px and pi 2 Py, then only to sigma 2 Pz, and Z always form sigma bond only. Pz always form sigma bond only. Similar to this same order we have to draw for our antibonding, that is pi star 2 Px, pi star 2 Py. Above that sigma star 2 Pz. Here also one orbital will come. So we'll see how to fill. One electron from here filled, one electron from here. So pi 2 Px filled, pi 2 Py. One electron from here, one electron from here filled. Pi 2 Px equal to pi 2 Py filled. Then only we can move to sigma 2 Pz. So one electron left here, one electron left here. So sigma 2 Pz also filled. And the bonding orbitals are not filled. Okay. So what will be the bond order? That is half Nb minus Na, isn't it? So if you take bonding orbitals, here we can see sigma 1s2 is filled, sigma 1s2 is filled, sigma 2s2 also filled. So if we calculate the bond order, sigma 1s2, it is will be the like configuration sigma 1s2, sigma 2s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, then pi 2px2 equals pi 2py2, sigma 2pz2. This will be the configuration of our N2 molecule. So number of bonding, so we have to calculate the number of bonding atomic orbitals and molecular orbitals. So 1, 2, then here pi 2 px2, pi 2 py2 and sigma 2 pz2. How many will be that? 2 plus 2 plus 2 4, 4 plus 2 6, 6 plus 2 8, 8 plus 2 10. So 10 minus antibonding 2 4. Sigma star 2s2, then sigma stars to 1s2, sigma star 2s2. So 10 minus 4 by 2 will get 6 by 2, that is 3. Bond order is 3. Similar method we can calculate with, we can draw the energy diagram with other molecules also. So I hope all of you understood this topic.